So now we shall continue our discussion on the Z transforms. So in the last class we saw that uh, how do we compute the Z transform for the sequences and what is the relationship between the Fourier transforms and the Z transforms. So the most useful property of the Z transform is that whenever we have the infinite sum, and if it can be expressed in the closed form in the, say for example, x of z has some rational function of these two polynomials p of z and q of z. So if you have so whenever your infinite sum can be expressed in the closed form, then it is most useful to analyze the LTI system, which we will see later on. So whenever we represent this in the form of a rational function, we also define that this rational function is defined inside some ROC, the region of convergence. Okay? So let's recall a couple of points before we see some examples of how to compute this region of convergence and also the Z transform. So first of all, the values of Z for which you have x of z is equal to 0, we denote all those z's as the zeros of the system, and values of z for which you have xz is equal to infinity are defined as the poles of that rational function. Okay, so we will use these notations later on when we study more about the computing the response of the system. Okay, so let's see one of the example, which we denote this as a right-sided exponential sequence. Okay, so suppose this sequence is given by x of n as a to the power n un. We call it the right-sided sequence because this sequence is non-zero only for n greater than or equal to 0 because of this step input, right? Because of this step signal, which takes value 0 for n less than 0. So that's why this signal or this sequence is a right-sided exponential sequence. Now computing the x of z by using the formula we discussed the last time, then we have summation from minus infinity to infinity of a to the power n un z to the power minus n, which I can represent because we have this un, so we can take this summation instead of from minus infinity to 0. So n is equal to 0 to infinity and a z inverse n. Now for this to converge, we want that a z inverse should be less than 1, or we say that mod of z is greater than mod of a, which is the region of convergence, and in the complex plane it is basically some circle. This is the real part, this is the z plane, and this is the imaginary part of the z. So let's say we have some this circle of some radius a, so the region of convergence is all this portion which is greater than a. Okay? So in that case we can represent your xz as a rational function as 1 upon 1 minus a z inverse, or after simplification z upon z minus a, with the region of convergence mod of z greater than mod of a. Okay. So now see a couple of points. So if you have mod a less than 1, then the Fourier transform converges to x of e to the power j omega, because when we have mod of a less than 1, it means the unit circle is included. So x of e to the power j omega is equal to 1 upon 1 minus a e to the power minus j omega. On the contrary, if we have mod of a greater than 1, then the Fourier transform doesn't exist. Okay, so for a particular region of convergence, uh, we can compute the Z transform. So in a similar way, there are a couple of sequences which you can use this as a table. That for the impulse sequence, you have the transform 1, and the ROC is the entire plane in the Z plane. When you have the step sequence, you have this transform where your ROC is mod of Z greater than 1. So this is a right sided sequence, this is a left sided sequence, meaning to say that it is non-zero for n less than 0. So for this we have mod of Z less than 1. So there are these standard sequences which you can use to compute the transform, but mostly we will see the use of them when we will talk about the inverse Z transform. So in a similar way, what we have done for computing the inverse Fourier transform, we took the partial fraction approach, and then from a table we can compute this inverse transforms. Okay, so now let's discuss some properties of the ROC, because we saw that the ROC plays an important role whenever we are defining the rational function. So most of the time, the first property says, so most of the time you will see that either the ROC is defined by mod of Z greater than some RR which is less than or equal to 0, or mod of Z is less than RL less than equal to infinity. And we will see the significance of this one, because generally RL is the left sided sequence and RL is for the right sided sequence, or we define as annulus. That is, you have mod of Z lying between RR and RL, which is greater than equal to 0 and which is less than equal to infinity. So this is some annulus. Okay. Now the second property says that Fourier transform of xn converges absolutely if and only if the ROC of the Z transform of xn includes the unit circle. So this was the main point of discussion of the last class, and this is the property because it converges absolutely, and this is a necessary and sufficient condition that you have your ROC of the Z transform including the unit circle. Okay, it's about the unit circle. So the third property says that ROC cannot contain any pole. Cannot contain any pole. And we saw above how to compute the pole. So if you try to think a bit onto this, we saw that the Z transform reaches to infinity. The poles are based on the definition of the pole. The Z transform reaches to infinity. So the ROC cannot contain any pole. Now the next property says that if xn is of finite duration, then the ROC is the entire Z plane. The entire Z plane. Except possibly Z equals 0 or Z equal infinity. Okay, for finite duration sequences, ROC is the entire Z plane. So we'll talk about this property. So this is quite important property when we talk about the properties of the Z transforms. Now if your xn is a right-sided sequence, meaning to say that it is 0 for n less than n1 less than infinity. Okay. So the ROC of such sequences extends outward from the outermost finite pole in xz to z is equal to infinity. Okay. Now if you have xn is a left sided sequence, meaning to say that you have a say sequence 0 for minus infinity and 2 less than n. Okay. So in that case your ROC extends inward from the innermost non-zero pole in xz to and possibly including z is equal to 0. Okay, we shall see the graphical description of this property a bit later. Now if x of n is a two-sided sequence, by a two-sided sequence we mean that it is of infinite duration. Right? In that case the ROC will consist of a ring in the z plane bounded on the interior and exterior by a pole and not containing any poles but. Okay, so let's see. So any infinite two-sided sequence first of all can be represented as a sum of a right-sided part and a left-sided part. Okay, so this is the two-sided sequence which can be represented as a summation of both-sided sequence, for which the ROC, like we said, it's a ring. So let's say mod of z is lying between RR and RL. Okay. Now if you have RL less than RR, then in that case your Z transform won't exist. Okay, we can see this by an example. Let's say some sequence is given by your 1 by 2n un minus 1 by 3 of to the power n u minus n minus 1. So you will see that this part is a left-sided sequence and this part is a right-sided sequence. Okay. So on computing x of z for this sequence, we will get for the first part as 1 over 1 minus 1 by 2 z inverse, whose ROC is mod of z greater than 1 by 2, and by using the same formula as we had seen here, plus the z transform of the second term is 1 plus 1 by 3 z inverse, whose ROC would be mod of z less than 1 by 3. Okay, so let's see on the z plane. Okay, so we have that circle which is 1 by 3 and we have 1 by 2. So it says that mod of z is less than 1 by 3 is this region on the z plane. And for this part it says for mod of z greater than 1 by 2. So there is no common region between the ROC. So it is a bit difficult to compute the, it's not possible to compute the Z transform. Okay, so because there is no overlap. So some of the property we had seen earlier, we talk about the poles. So the next property says that the pole 0 pattern does not completely specify the Z transform of a sequence. The ROC must also be specified. So knowing only the knowledge of poles and zeros, you cannot completely specify the Z transform. You must know the ROC. So we can see one one case. Let's say so what do we have, that this is some unit circle and two poles are inside of this unit circle as sorry, A and B, and another pole is outside, which is C. So the ROC can be of four types for this particular case. The first one is we have the let's say this circle where these are the AB and this is the C. Okay, and we have the outward ROC region, which was about the property when you have the right-sided sequence. So the ROC extend outwards from the outermost finite pole in XZ to Z is equal to infinity. Okay. The second case would be so these three are ABC and it's the inside region of the ROC is the ROC, which is valid for the left-sided sequence, which says that the ROC extend inward from the innermost non-zero pole in XZ to possibly Z is equal to 0. The third case, it could be a ring A, B and C, right? So the ROC is this region where you have mod Z lying between A and B. And this was for the two-sided sequence. Now the next case, since we have three pole location, so we can have another circle which is between the B and C. So this is the region where you have mod of Z lying between B and C, and for here you have mod of Z lying between A and B, where A, B, C are these location of the poles. So these four cases are possible depending on this location of our poles. So pole 0 pattern does not completely specify the Z transform per sequence. The ROC must also be specified. So note this point always. So I think we can continue with the inverse Z transform in the next class, and we keep it simple to the properties of the Z transform. Okay.